I've not been working on these lambda bar mu tilde things for a number of years, but fortunately, in what I'm doing now, which is a bit far away from proofs and a bit far away from programming, I met this kind of things in some joint work with Jovana Obradovic, who was originally from Novi Sad, which we heard from Sylvia. And this is the story I want to tell you. So you will have to bear with elementary things that have to do with unrooted trees. Okay, so an unrooted tree is a graph where you don't have any loops, like drawn here. And it's interesting for mathematicians because instead, well, I would prefer to have the mic. Yeah. So it's interesting for mathematicians because, well, at each node you could place some kind of mathematical object. So here, the mathematical object which is represented is a triangulated surface which has lots of triangles. And you might be interested in, if you have two neighboring nodes, you might be interested in picking. So each, well, the edges coming out of the node are exactly all the triangles of the node, which is this surface. So you could be interested in the edge is singling out one particular triangle of the surface, say in A1 in the picture here. Well, my ones, and yes, it's a 1. And a particular triangle in the surface sitting at A4. And then you can glue them together. Okay, this is topological operation that you can do easily. Okay, so this structure has a name in mathematics. If you can do that, if you have operations that you can plug together in this way, then you have something called a cyclic operat. Okay, but you don't need to know these words. So there is a notation for this. I say that I compose node A1 with node A4 along X and X bar. Okay, so here I need, again, to do a little distinction. In such a graph here, you see a difference between what I call internal edges and leaves. So leaves are like shown out of A2, there you have two leaves. So the leaves are not connecting any two nodes, but just entries of a node. So, and why do I give two different names? Because actually, I consider that every operation has a number of entries. So, for example, A1 has 3 entries, and I just named the one in green, which is X. But I should have given names to all the entries of all nodes. Okay, so far so good. So now, the important property that mathematicians want to have, or maybe I could have told this at this level, the mathematicians want to be sure that if they start to do this game, composing two nodes, which corresponds more or less to contract this green edge, in whichever order you do this on the whole tree, you might have started by composing A1 and A5, etc. Whatever order of composition you chose, you end up building the same strange rabbit with a hat on top of it, of his head. Well, and many more things, because this is only what happened in the green contraction. Okay? No, this is not. This is already done. Okay, so there are theorems in this talk. There will be 3 theorems. And they all say the same thing in different languages. So the question the mathematicians want to make sure, so here, this idea that you do things in a certain order is represented by these red circles. So if you read it, it says, for example, compose A1 and A3. Well, that's a new thing. Then compose with A2. That's a new thing, etc. And on the other side, you tell a different story. So all such circlings should be equal. They should result in the same final outputs, final operation. And there is a theorem which says that this is true only if you can make these local changes, which are on the left here. And if you look at these local changes, they tell you that this composition operation, which is written here, is associative and commutative. You don't mind composing this rabbit and its future hat in one way or the other. Okay? So that's all. Theorem, provided you have these two equalities in blue here, then all the possible circlings in the tree result in the same operation. And this is, in mathematics, this is called the Coherence Theorem. So if somebody in the audience is familiar with monoidal categories, it's a theorem in this style. Okay. So now, how do we prove this theorem? So there are probably ways to prove it directly, but I like an indirect proof. And my indirect proof is to enrich the possibilities of decomposing a tree in another way. So in the previous way, what I was doing is I was taking an edge and separating the tree in two subtrees. That should be visible in the picture. You take an edge, you compose the two things on the left and on both sides of the edge. But you have another way to decompose a tree, which is to take a node and then at once to compose all the trees that have entries in this node. So this now results in blue squarings like this one. And it results in another syntax. The syntax, well, I don't insist because of lack of time, but the syntax is like the usual syntax of terms. Okay, so it starts by saying A1 here, and then from A1 you have several subterms. But beware that the next term might not be a neighbor of A1. So for example, after A1, I could pick, like in the picture, I could pick directly A6. This is legal here. Okay, so I have this other language. And, okay, so then I also ask myself, are all these squarings, possible squarings, giving me the same result? And the answer is yes, provided there is one equation satisfied, which essentially says that if you pick a node A and then a node B, you could have picked first a node B and then the node A. So on the left, you've picked A first and then B. On the right, you pick B first, and then inside this subterm, you pick A. Okay, so again, you have a coherence theorem, that's theorem 2. Okay. So, what do I have here? Okay, so my strategy here is that I want to prove theorem 1 thanks to theorem 2. So believe me, theorem 2 is not difficult to prove because essentially it's about exchanging nodes. And the argument is quite easy. Theorem 1 is a bit more tricky, and the idea here is that we are going to merge, this is the fundamental slide of the talk, we are going to merge the two ways of decomposing trees into one single syntax, okay, which mixes the two styles. And here, we are going to use, in order to merge the syntax, we are going to use the mu syntax. Okay, so composition along x and x bar is going to tell me, okay, I have my operation A, it has some special entry x. Let me single this out. So this is mu x dot this operation. And the other one, x bar, the same. So the composition AB becomes a mu-mu pair. Okay, no mu tilde here, I'm sorry, because everything is self-dual here. There's no logic. I'm sorry about this. Okay, so just mu. And same thing, when in the second syntax, when I was, in the second syntax, when I was plugging subtrees along an entry, I said, well, I plugged the entry x along the entry x bar of the other tree. And again, this results in a mu. So this new syntax is here, and the fundamental point is that we introduced these magical commands, okay, from the mu-mu tilde calculus. Okay, so next thing, tell me how much? 5? Okay, good. Okay, so of course we have the third theorem here. We have mixed the two. So whatever we can write with this new syntax, and here, well, I should be a bit careful. It's a bit like in the talk of Delia on proofnets. These terms make sense only relative to a certain tree. The tree behind is always the same. And these are just ways to show decomposition of these trees, where now you have both blue and red things, not just red or not just blue. Okay, so the theorem says that, now this is the proof. The theorem says that that's the third theorem. If you have this mixed syntax, then again, all terms are equal, provided, that all terms are equal is provable from just these two equalities. And these two equalities, well, the second one is something like we've met before. And combining the two rules, so the first rule says that it is commutative. Combining the two rules from this single rule, we get the famous critical pair that we have seen in Sylvia's talk. Okay, so now, interesting thing is why was it interesting to have these three syntaxes while we wanted to prove only a theorem about the first one? Well, this is because, and here I will be sketchy in order to save time for the last slide. So I'm not good in ordering. Okay, so I just give you the structure of the proof. First, we prove theorem 2. Believe me, it's not too difficult. Then we prove theorem 3. Sorry. There was an important remark before. There is a nice connection. No, that's a conclusion. Yes. Here. Once we have oriented the rules in this calculus, so we have a notion of rewriting, we have normal forms, because each time we remove a mu, and we never duplicate anything here. Okay, this is linear. I will come back to this at the end. So, an interesting remark is that the normal forms correspond exactly to the blue syntax. And then the anti-normal forms, what are the anti-normal forms? That are the terms that are not reducts of any term. Those are exactly the red terms. Okay, so it's interesting because the mixing of the two syntaxes fits well with the rewriting system. Okay, so now back to the main plan of the proof. First you prove theorem 1, then you prove theorem 2. No. First you prove theorem 2, sorry. Then you prove theorem 3. Thanks to the fact that you prove, well, okay, thanks to a lemma. At this stage I cannot go into the details. And then you prove the last theorem. Okay. And you nicely connect the three equational systems. So lemma 1 relates two equational systems, and lemma 2 relates to the two other ones. Okay, so I will not go too much because time is running, and I will finish with the remarks. Okay, so yes, as I said, the mathematical structures involved are called cyclic operats. Okay, then what is interesting is the link with the mu tilde syntax is that we know already from many people that the problem in classical logic is this famous critical pair in connection with contraction and weakening. But it is also known, very well known, that linear logic solves this issue by being linear or by controlling what is not linear. And here we are in a linear setting. Okay? And in the classical setting, what was very, very wrong with classical cut elimination was that in the end we were equating all proofs. And this was not good, because we were also equating first and second projections. So we were exactly saying that everything was not proof relevant. In linear logic, we don't have this. And in our situation, we don't have this either. And the fact that we have many normal forms is actually meaningful in this context, because we say exactly the same thing. All proofs are equal. But in this case, it means all decompositions of the tree. This is very safe, and it states an interesting mathematical result.